This video is meant to help with, continue helping with exercise 232, where we're drawing resonance structures for some different compounds. And these compounds will have more than one of the 5 resonance patterns, most of them. Now, the last video ended with E, and I started to make a video for F, for the molecule in F, and when I got to the 9th resonance structure, I decided that this exercise was more complicated than you would ever have time to do on a test, and it's also, I think, more complicated than you would need to really understand the meaning of resonance, which is what I'm trying to communicate to you guys. So you don't have to worry about this exercise. You could just put NA, not applicable. And that's because you don't need to draw all of these resonance structures in order to see these patterns. What you want to get out of this chapter is to be able to see the 5 patterns and to know what they mean. They make a molecule more stable, more rigid, and they allow you to see charges in places you otherwise may not have. So you can just write not applicable for that problem. Skip over it, and we'll go on to G. Let me take this pattern table with me. Alright, so we've got this. Now, with this molecule, we're going to go one pattern at a time, and before we look at them, let's just draw all the lone pairs in. Carbon only has a lone pair when it has a negative charge. None of the carbons here have that, so none of them have a lone pair. So we only have to worry about the nitrogen. It already has 6 electrons around it, 2 in each bond, so it just needs 2 more. So it just has 1 lone pair. Okay, is this lone pair allylic? It's not. In order to be allylic, you have to be 1 atom away from a double bond, and there's no double bond in that molecule. So it is not allylic. Is there an allylic positive charge in that molecule? There's not. There is a positive charge, but it's not allylic because it's not 1 atom away from an atom in a double bond. So we don't have an allylic positive charge. How about an allylic lone pair? I'm sorry, how about a lone pair adjacent to a positive charge? We do have that. This lone pair right here is 1 atom away from an atom with a positive charge. So this is a resonance pattern. So we definitely have resonance, so we'll draw those big brackets that warn people that all the structures that we draw inside of them, no individual structure is the true structure. The true structure is the average of them all. So we'll draw our first molecule here. And the curved arrow pattern that goes with this is anytime you have a lone pair adjacent to a positive charge, the lone pair goes to form a pi bond toward the positive charge. Let me make that more clearly onto that bond. So, also, just so we can calculate formal charges a little more easily, I'm going to draw the hydrogens in. Notice the carbon with the positive charge has no hydrogens on it. Okay, so to draw the resonance structure, we'll just draw that special resonance arrow, and we're just going to copy and paste this. So copy, so we have that over here. Alright, so anywhere we have the tail of a curved arrow, that is a place where electrons are moving away from, so we're going to erase those electrons. And anywhere where you have the head of a curved arrow is a place where electrons are arriving. And if the head of a curved arrow is pointing at a bond, then the electrons arrive as a bond. So you draw them in as a bond there. If you calculate the formal charges here, you'll see that the nitrogen has a positive charge now, 5 minus 4 lines, and the carbon has no charge. So we're going through this left molecule, and we've been through the first 2 structures, the first 3 resonance patterns. We just drew the resonance pattern you get from that 3rd pattern. But we want to go through all five. Is there a pi bond between atoms of differing electronegativity in that left structure? No, there's no pi bond there, so we don't have that. And last but not least, we don't have a conjugated pi bonds in a ring, because we don't even have a ring there, so we couldn't have that. So we went through all the five patterns for that leftmost structure. Now we want to do the same thing for the structure on the right. So this one. Is there an allylic lone pair there? There's not. There's no lone pair at all. Is there an allylic positive charge? We have a positive charge, but it's on an atom in a double bond. It's not one atom away. So that's not allylic. Do we have a lone pair adjacent to a positive charge? No, we don't have any lone pairs there. Do we have a pi bond between atoms of different electronegativity? We do. Nitrogen is really electronegative and carbon's not, and we have that pi bond between them. And so we'd want to draw that pattern. Notice though, for that pattern, the pi electrons go onto the more electronegative atom, and if you draw that, you'll just end up with the structure you have on the left. So we do have that pattern, but we've already drawn the structure that it would give us. And we don't have conjugated pi bonds in a ring, we don't even have a ring. So these are our only two resonance structures for this molecule. And what they mean, let me just resize these brackets. And the fact that you have resonance here is telling you that this molecule is more stable than a molecule that doesn't have resonance, or than this molecule if it didn't have resonance. It's more rigid, because what looked like a single bond that could rotate is actually something in between, something that has a partial pi bond that can't rotate. And it allows us to see charges in places we might not have seen. So the true structure would look something like this, with a slightly positive charge on the nitrogen, slightly positive charge on the carbon. And just to clean this up, because it's a bond line drawing, you'd erase those hydrogens, those are implied. Okay, and you do that to the other structure. The main structure, the resonance hybrid would look like that, and you would get that by averaging those two molecules. Alright, let's go through the same pattern, same sort of method of thinking for this next structure. Alright, first let's draw the lone pairs in so we can recognize these resonance patterns more easily. None of the carbons have lone pairs because none of them have a negative charge. And the nitrogen already has 3 bonds, so 6 electrons around it. So you just need to add 2 more, 1 lone pair. Okay, is there an allylic lone pair in the molecule? There's not. We have a lone pair, but it's on an atom in a double bond, not 1 atom away. Allylic means 1 atom away from an atom in a double bond, so we don't have that. How about an allylic positive charge? We don't have a positive charge. How about a lone pair adjacent to a positive charge? There's no positive charge in that drawing. How about a pi bond between atoms of different electronegativity? That we do have right here. Every bond after the first bond is a pi bond, so we have a pi bond there between a carbon and a nitrogen. Nitrogen is much more electronegative than carbon. So we will have resonance in this structure, so we draw those big brackets to warn people that each individual structure we're drawing is not the true structure. The true structure is the average of them all. So here we've got, just copying that structure down. Okay, and the curved arrow pattern for when you have a pi bond between atoms of different electronegativity, the curved arrow pattern for that is that the pi electrons go onto the more electronegative atom. So I'm going to draw the hydrogens in on the 2 atoms whose formal charge might be changing, that carbon and the nitrogen. The nitrogen doesn't have any hydrogens. And so you draw the special resonance arrow that tells you to take the average of the molecules inside the brackets. And here, anywhere where there's the tail of an arrow, those are electrons that are moving away from there, so you erase those. Anywhere where there's the head of an arrow, that's a place where electrons are arriving, so you draw them in. If the head of a curved arrow is pointing at an atom, then you draw those electrons as a lone pair. Oops. I'm sorry, this original structure should only have one hydrogen because it needs a total of 4 bonds and already has 3. So this has just one hydrogen there. Okay, if you calculate the formal charges now, you will see that this carbon has a positive charge, 4 minus the 3 lines, and nitrogen has a negative charge, 5 minus 4 dots and 2 lines. Okay, so we went through the first 4 patterns for this left structure. If we look at the 5th pattern, we don't have that because we don't have a ring at all, so we couldn't have conjugated pi bonds in a ring. So we went through all 5 structures for that, we went through all 5 patterns for that left structure. So now we just need to do the same thing for this molecule on the right. Does that have an allylic lone pair? It doesn't, because although we have a lone pair, we don't have a pi bond that it's one atom away from. For the same reason, you can't have an allylic positive charge, we just don't have a double bond in the molecule. Do you have a lone pair adjacent to a positive charge? That we do. This lone pair, these lone pairs right here are one atom away from an atom with a positive charge. So the curved arrow pattern for that, though, brings the lone pair back to form a pi bond. That would leave you with your original structure. So we have that pattern, but we've already drawn the molecule that it would give us. We don't have a pi bond between 2 atoms of different electronegativity in that right structure because we don't have a pi bond, and we don't have alternating single and double bonds all the way around a ring. We don't even have a ring. So this molecule just has these 2 resonance structures. The true structure never looks like this, never looks like that. It always only ever looks like the average of the 2, so that would look something like this. And the nitrogen would have a slight negative charge, and the carbon would have a slight positive charge. And the fact that the molecule has resonance means it's more stable and more rigid. Alright, going on to I. So first let's draw the lone pairs in. We have 2 lone pairs on the oxygen and just 1 lone pair on the nitrogen. That gives everything a total of 8 electrons. And now we can look for patterns. Do we have an allylic lone pair here? We do. This lone pair on the nitrogen is 1 atom away from an atom in a double bond. So that lone pair is allylic. So we know we have resonance, and we can draw those big brackets to warn people about the resonance we have, to warn them that all the structures we draw, none of the structures we draw are the true structure. The true structure is the average of them. The average of them all. Okay, so that's our structure. Whenever you have an allylic lone pair, the allylic lone pair goes to form a pi bond toward the existing double bond, and the pi electrons in that pi bond go onto the more or go onto the atom in the double bond that's further away from the allylic lone pair. So we draw that special resonance arrow that tells you to take the average of those. Oops. The average of the structures. And here, anywhere where there's the tail of a curved arrow, those are electrons that are moving away from there, so you erase those. Anywhere where there's the head of a curved arrow is a place where electrons are arriving, so you draw those in. If the head of a curved arrow is pointing at a bond, then you draw a bond. Likewise, anywhere where you have the tail of a curved arrow, those are electrons that are moving away from there. Anywhere where you have the head of a curved arrow, that's a place where you have electrons arriving, so you draw them in. If the head of a curved arrow is pointing at an atom, then you draw those electrons as a lone pair. And you'd see that the formal charges here are a positive charge on the nitrogen and a negative charge on the oxygen. Alright, so we're going through the 5 patterns for that first leftmost structure there. We saw that we have an allylic lone pair. We drew the structure for that. Do we have an allylic positive charge? No. We don't have a positive charge in the molecule at all, so we don't have an allylic positive charge. Do we have a lone pair adjacent to a positive charge? No, no positive charge. Do you have a pi bond between atoms of differing electronegativity? We do have that. This pi bond is this pi bond here between the carbon and the oxygen, the second bond there, is between two atoms with different electronegativity. Oxygen has a huge electronegativity. It's very electronegativity, and carbon is just average. So we're going to have another resonance structure coming off of this one. Whenever you have that pattern, the curved arrow pattern that goes with it is that the pi electrons go onto the more electronegative atom. So here, any place where you have the tail of a curved arrow, those are electrons that are going to move away from there, so you erase those. And anywhere you have the head of a curved arrow is a place where electrons are arriving, so you draw them in. If the head of a curved arrow is pointing at an atom, then you draw them in as a lone pair. And in this structure, if you go through the formal charges, you'd see that the carbon now has a positive charge, and the oxygen has a negative 1 charge. Formal charge. Okay, so we're still looking at this molecule. We've gone through the first 4 resonance structures. For the 5th one, we don't have alternating single and double bonds in a ring. That's what it means to be conjugated. And so all the way around a ring, and so we don't have that 5th pattern. We don't even have a ring, so. Okay, let's go through the same 5 patterns with our second structure here. Do we have an allylic lone pair here? We do. We do have an allylic lone pair. These lone pairs are 1 atom away from an atom in a double bond. So those are allylic. But if you were to draw the curved arrow patterns for that, with those lone pairs going toward the double bond, and the pi electrons going in the atom in the double bond that's further away from the allylic lone pair, you would see that would just bring you back to your original structure. So, although we do have that pattern, we've already drawn the molecule that it would give us. Okay, next, do we have an allylic positive charge? We do not. We have a positive charge, but it's on an atom in a double bond. It's not 1 atom away. So we don't have that pattern. Do we have a lone pair adjacent to a positive charge? We don't. Our lone pairs are not adjacent to a positive charge. They're 2 atoms away from a positive charge. And so we don't have that pattern. Do we have a pi bond between atoms of differing electronegativity? We do actually have that. This pi bond here is between a nitrogen, which is really electronegative, and carbon, which just has an average electronegativity. So, you would have a pattern there, but notice what happens if you were to draw the curved arrow pattern for that, where the pi electrons go onto the more electronegative atom. You would end up with this structure we drew down here. And so, although we have that pattern, we don't have to draw anything new for it. We've already drawn the structure you'd get for it. Because we don't have conjugated pi bonds in a ring, we don't have this 5th pattern. We don't have a ring at all, so we couldn't have that. So we've gone through all 5 patterns for this second structure. Last but not least, we just want to go through all 5 patterns for our third structure here. So, do we have an allylic lone pair here? No, we don't have a double bond, so nothing can be allylic, so we also don't have the second pattern. Do we have a lone pair adjacent to a positive charge? We do, in 2 places. This lone pair is right next to the positive charge. Notice, though, that if that were to come down towards it, you would end up with this structure, so we already have that drawn. These lone pairs are also right next to the positive charge. Notice, though, if those were to come towards it, they would form another structure we've already drawn. So we do have that 3rd pattern, but we've already drawn all the structures that we'd get from it. Okay, going back, does this molecule have a pi bond between atoms of differing electronegativity? It does not. It doesn't have a pi bond at all. The pi bond is always, the first bond you make is always a sigma bond. Pi bonds are every bond after that. We only have single bonds there, so those are all sigma. And we don't have conjugated pi bonds in a ring because we don't even have a ring, so we have that. So these 3 structures are the only 3 resonance structures for this molecule. The true structure is the average of the 2. It would never look like any one of these individually. It would always only look something like this. Something like that, with intermediate bonds here, and because those have partial pi bonds, that means those bonds can't rotate, so the molecule is more rigid, and with charges that are spread out rather than localized in one place, which makes that molecule more stable.